Hello again. Let's discuss the idea of combining this k-means clustering stuff with PCA, with principal component analysis. Um, in general, high dimensionality is bad. I've used the phrase curse of dimensionality before. You don't call something a curse if it's a good thing. And in particular, high dimensionality makes distances less meaningful. That's just kind of intuitive, right? I mean, how do you, when we're talking about distances, in this context, we're talking about the square root of these distances squared, which is if you were if when we covered the sums of squares stuff, if you were asking yourself, wait, why are we minimizing the squares? Well, it's because there are these squares in the distance formula, and the square root is monotonic. So minimizing this distance, minimizing the square root, is the same as minimizing the sum of squares. And in general, some dimensions matter and some dimensions don't. I mean, the more dimensions you have, the more noise there's going to be. And just thinking through this, admittedly, pretty informally, but suppose only one component matters. Suppose only the second component matters. Well, here the components that matter are 1/3 of the vector. If we add a bunch of other stuff, suddenly this component we actually care about is 1/7 of the vector. So obviously a pretty informal way of thinking about it. But the more dimensions there are, the more noise there are, and the harder it is to retrieve useful information. And this applies to clustering. The more dimensions there are, the harder it is to find clusters. So here's a question or a statement followed by a question. We have a way of reducing dimensions. We can replace our current axes with the first few principal component axes, and we can reduce the dimension that way. And obviously, there's a cost to this, where changing coordinates, we are um, now trying to explain variance if we're looking at PCA. We're losing data. I mean, I've said that 70% you sometimes see as sort of a target. So we're maybe potentially losing 30% of the information about variance. But this does reduce dimension, and we've seen that high dimensions are bad. So here's a question for you. Should we perform PCA before we perform k-means clustering? I guess I should say before we perform Lloyd's algorithm, but before we look for the clusters. And the answer to this question is maybe. Um, Sorry that I don't have something more satisfactory for you. Um, the reality is that in data analytics, you don't have a lot of theorems saying, yes, definitely do this. There's no theorem that says you should do PCA first because it will speed k-means up by 20%. There's no theorem that says you should do PCA first because it will reduce error by 2%. Um, what we have instead of theorems is sort of, well, experience. People do things and they look at certain data sets and they ask, well, does this thing help or hurt on that data set? And from that, we get sort of vague guidelines and rules of thumb. I would say that doing PCA before we do k-means clustering is fairly common. A lot of people see benefit from it a lot of the time. But again, that is different from a blanket statement that you should always do it. You're not going to see a whole lot of blanket statements like that in a big data course. So the code is all on Canvas, and there's not a lot of really new stuff here, so I'm not going to dwell on it. But since I floated the idea that we might do dimensionality reduction before any sort of k-means algorithm, let's take another look at this penguin data set. Copy and pasted straight from Canvas. So if we do PCA on the penguin data set, well, first we should scale it with standard scaler. And then we need to decide how many dimensions we're going to keep. So let's take a look at a scree plot. In terms of variance, even one component is explaining a lot of variance, but the elbow of the scree plot is at 2, so let's keep 2 principal components. Well, now we can perform the PCA. We've seen this before, and I think messing around with code, hands-on is more productive than watching a video on it in Canvas. We've seen PCA before. It's pretty self-explanatory syntax, which saying that probably means I've broken things somehow. But let's run it and see. Let's run it and see. Tum, tum. Okay, yeah, work just fine. I've been doing some stuff for the next week, and stuff takes a while in next week's code. There are some delays. This happened so fast that I sort of thought something was going wrong. But no, it's the Penguin data set is just very small. So it happened very quickly. Once we have performed PCA, we can perform k-means clustering. Uh, okay, now we've got some kind of error, which I am not going to try to troubleshoot live. Let me pause this. I mean, once I looked at the error, it was not hard to diagnose. You see that k-means is not defined, which means that I did not import it. So now I have, and this is running. This sounds kind of scary. You're going to get this error. You can ignore it. So, well, we've performed our clustering. I guess we'd better take a look at it. And I am just going to come to canvas and show the scatter plots here. So this is the result of k-means clustering on the PCA reduced data. We only ended up using 2 dimensions, so we can perfectly and completely plot this. Just looking at this, is this any good? Well, again, is this any good? Is such a hard question to ask because it insinuates that we have an end goal, and this is unsupervised learning. I mean, is it any good in the sense that k-means clustering worked and we found 3 clusters? Yes, it's good. Since we have some intuition about these clusters, since we sort of expect that they might correspond to species, I guess when I say, is it any good, what I really mean is, do these clusters correspond to species? And the answer is that one of the, yes, sort of. Um, we can take a look and we can look at the actual species. And we can see that this cluster down here does a very good job of representing Gentoo, don't know how to pronounce it, but a very good job of representing this penguin species. The results here are more mixed, or rather, bad joke incoming. But here, the penguin species are mixed, as you can see. Here, they aren't. Here, we now just have a very solid line between the species. So we definitely lost something thing when we did k-means, especially if we go back here. I mean, if we're not doing k-means, we can't look at all four dimensions at once. So here is just two dimensions at once. Here are the actual species. Here are the clusters that k-means gave us. And you see here, you know, the the actual species are mixed together, but when we do k-means clustering, we do a very good job of identifying that. And and the reason that happens is again that there are really four dimensions. So you might look at this point here and you might say, well, this point is surrounded by Adelaide. So surely the clustering algorithm is going to put it into the Adelaide cluster, but that doesn't happen. It's put in the Chinstrap cluster. And that's because this is only surrounded by Adelaide in these two dimensions. If we could look at all four dimensions, it would be close to some chin strap penguins, some other chin strap penguins, and that would allow us to get into the chin strap cluster. Again, I'm speaking about this very loosely. There is no chin strap cluster. There's a cluster that seems to roughly correspond to chin strap penguins. Here, nothing like that can happen because these dimensions are all that we have. So if what point was it? I mean, you can't tell, but maybe it was this one. This point is close to the other Adelaide penguins in these two dimensions. These two dimensions are the only dimensions that we have. So of course it winds up in the Adelaide cluster. Um, So, I mean, I guess if you just to look at this little toy example, you might say, well, that sucks. I mean, we seem to have done noticeably worse and not really gotten much in return. But that's just what happens when you teach big data methods and big data techniques on small data sets. I mean, the reason we didn't get much in return here was that the original data set was already low dimensions. Four dimensions, not a lot of dimensions. If we had, 10,000 dimensions to start with, and we managed to get that down to two, then we would be seeing benefits to counteract the trade-offs.